Okay, in this video we're going to be looking at the standard normal distribution. What we'll do here is use the standard normal distribution table to find probability values, and also we'll be trying to find out what the z-values are given the known areas. Okay, the definition of a standard normal distribution is a normal distribution where the parameters are this. Mu, which is your population mean, that's equal to 0, and sigma, your standard deviation, is going to be 1. Okay, so this is what a standard normal curve looks like. Okay, and also the area underneath the curve is going to be equal to 1. So here, the horizontal axis is your z-score. The area that's underneath the curve is always going to be 1. Now, in all cases here, when we're trying to find, when we're using the standard normal distribution, when we're trying to find the area, it's not going to be easy to do manually. However, we have to use one of two things. We can use technology, which is the TI-8384 Plus calculator, or StatDisk, or Microsoft Excel, or other statistical software that does the normal distribution. And then second, we can use table A-2. So in this video, we're going to be using table A-2 to find probabilities. So here, this is part of the table A-2, or the standard normal distribution. Okay, so if we use this table, this one's for positive z-scores, by the way, and the next one I'm going to show you here is for negative z-scores. Okay, because z-scores can be either positive or negative. Now, when we use this table, the standard normal distribution table, and your book calls it table A-2, and it's also table A-2 on the Cruiser, Campus Cruiser, for those of you who are taking my class online. Table A-2 is designed only for the standard normal distribution, where the mean is 0 and the standard deviation is 1. Okay, so we can only use this table when the mean is 0 and the standard deviation is 1. Second, it has negative z-scores and positive z-scores, as I just showed you. So, for those of you who are taking this online, when you print out your table A-2 or the standard normal distribution table, you'll see that it has two tables, one for positive z-scores and the other one for negative z-scores. Each decimal value that you see in this table, that represents the body of the table. And this is going to be very important, because at the top it does says cumulative area from the left. So these values in the body of the table represent the cumulative area from the left of that vertical boundary. So here's the vertical boundary at Z. So here, that shaded area to the left, that's your cumulative area from the left. Okay. And also, your Z values are on the left-hand side, up to the 10th place. The other digit, which is the 100th place, that represents these numbers across, because the number across denotes the 100th place on the top row. So like, for example, let's say I want to find the area to the left of 1.54. So here's 1.54, and I want the area to the left. So using this table, we're going to find 1.5. That's this part on the left-hand side. And then on the top, we find 0.04. That's this column here. So I read down that 0.04 column, and then 1.5 down 1.4, you'll see that it's 0.9382. So the area to the left of that z value of 1.54 will be 0.9382. Okay. Alright, so the next thing we'll talk about here is how to find those probabilities. And there is a correspondence between the area, and probability. Okay. Those probability values, those decimal values that you saw in the body of the table, that represents the area of the area underneath that normal curve. So there is that correspondence there. Now, there may be three situations that you might have to find. This first situation is this, where the probability of your z-score being between A and B. Okay? The two things you have to do, you have to first use that table to find the cumulative area to the left of A, and also use that table to find the cumulative area to the left of B. And once you've done that, you're going to subtract. So here you're going to subtract the cumulative area that's left of B minus the cumulative area that's left of A. Okay? So when your z value is in between the two and you're trying to find the probability, you find the cumulative area to the left of each one of those and subtract the larger probability minus the smaller probability. And then the probability where z is greater than A, well, let's think about this. If it's greater than A, then that means we're looking at the cumulative area to the right. However, the table gives the cumulative area from the left. So to find the cumulative area to the right, we have to do 1 minus the cumulative area that's left of A. Okay? Greater than means that it's the area to the right. Now the third instance, if your probability that z is less than A, well, less than A means the cumulative area to the left, which is exactly what this table gives. The cumulative area from the left. So that probability that z is less than A would be the cumulative area that's left of A. Okay? So now let's start off with how we can do some of these particular problems that are cumulative areas. Okay, so here's the first example here. And as you can see, pretty much I've already done it, but I'm going to go ahead and cover this up. Here we want to find the area of the shaded region, and the graph depicts the standard normal distribution with a mean of 0 and a standard deviation of 1. Okay, so in this case here's our normal curve, and the corresponding z value for that is 0.17. Okay, so now we're looking for the area to the left of 0.17. So this is where we use our standard normal distribution table. That 0.01 represents the z value that is on the left-hand side. The point that's 7, that's 0.07. which represents this part on the top row. And that's going to be this column here. So we find 0.1, and then read across and come down on the 0.07 column, you'll see that it's going to be 0.5675. So here, that probability that x is less than 0.17 would be 0.5675. Okay, let's look at the next example. Here we want to find the area of the shaded region, and the graph depicts the standard normal distribution of bone density scores with a mean of 0 and a standard deviation of 1. And here, this is our normal curve. Here, the z value that we're dealing with is negative 1.14. Okay? Now, the negative 1.1 represents the part that's on the left-hand side. Now, it's negative. The z-score is negative, so I have to go to the one that says negative z-scores. And then I'm going to find negative 1.1, which is right here. And then 0.04 that's going to be this column right here. So go across to negative 1.1 and then find 0.04. Find this intersection. You'll see that it's 0.1271. So in this case here, our probability that z is greater than negative 1.14. Now, I do need to mention that the 1.1271, that table says the area to the left. Okay? We want the area to the right. So in this case, we have to do 1 minus 0.1271. And when we do 1 minus 0.1271, you're going to get 0.8729. So the probability that z is greater than negative 1.14 will be 0.8279. So this is an example of a situation where we had the cumulative area to the left, and we had to find the cumulative area to the right. Here, table A-2 gives you the area to the left, but if you want the area to the right, you have to do 1 minus 0.1271 in this case. Okay. All right, let's look at the next example here. And in this case, we're going to find the area of the shaded region. And the graph depicts the standard normal distribution of bone density scores with a mean of 0 and a standard deviation of 1. And in this case here, we have two z-scores. And we're finding the shaded area in between the two z-scores of negative 0.87 and 1.22. Okay. Now you can see here for the z of negative 0.87, I have to use the one that says negative z-scores. So I find negative 0.8, which is, I need to bring that up, negative 0.8, that's about right here. And then 0.07, that's this column right here. So read across to negative 0.8, and then 0.07 you'll see is 0.1922. Okay, so for your z value of negative 0.87, your area is going to be 0.1922. Now for the other z value of 1.22, we use the positive z-score part, so we find 1.2 and then 0.02. Read across and down, you'll see that it's 0.8888. Yeah, 0.8888. 1.2 and 2 will be 0.8888. Okay. Since we want the area in between, we need to subtract. So in this case here, the probability that your z-score is between negative 0.87 and positive 1.22, we subtract 0.8888 minus 0.1922. And that will end up being 0.6966. Okay. So those were the three examples of where you had a area where you had to find the area in between two z-scores. One was the area to the left of a z-score and the area to the right of a z-score. Okay, now let's look at some more examples that are related to just that. Okay, here we go. Let's say we had this situation. Assume that a randomly selected subject is given a bone density test. A randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. And here you want to find the probability that a given score is less than 2.32. And here you want to draw and sketch the draw a sketch of the region. So here I have a sketch of the region that looks like this. Okay, the mean of 0 and the standard deviation of 1. 2.32 is to the right of 0. And we're dealing with a score less than 2.32, so we shade the area to the left of 2.32. Okay? And since we're dealing with an area to the left, we can use the standard normal distribution table and get that value from there. So find 2.32 as this. 2.3 is on the left-hand side. So here's 2.3. 0.02 is this column right here. So read across the 2.3 and then 0.02. That decimal value there will be 0.9898. And it is the cumulative area to the left, so that's what we're looking for in this case, the cumulative area to the left. So the probability that your z value is less than 2.32 will be 0.9898. Okay. All right. Let's look at another example. Okay. This next one is this. Assume the readings on thermometers are normally distributed with a mean of 0 degrees Celsius and a standard deviation of 1.00 degrees Celsius. And here you want to find the probability that a randomly selected thermometer reads greater than 1.29, and you're going to draw a sketch of the region. So here's the sketch of the region looking like this, where the mean is 0 and the standard deviation is 1, and 1.29 is to the right of 0. So we're looking at a thermometer reading of greater than 1.29. That's this green shaded area to the right. Again, we can use the standard normal distribution table, but it's going to give you the cumulative area to the left. We want the cumulative area to the right, so we want to subtract 1 minus whatever this cumulative area is on the left to get the cumulative area on the right. So let's find 1.2, and then 0.09. Here's 0.09, that's this last column here. So you read across to 1.2 and then 0.09. You'll see that it's 0.9015. 0.9015. So in this case here, we have to take that area from the left of 0.9015, subtract it from 1, and you'll get 0.0985. So in this case here, the probability that x is greater than, and I should say z is greater than 1.29. Need to correct that. Z is greater than 1.29. That will be 0.0985. Okay. All right. Now here's the next example. Assume that the thermometer readings are normally distributed with a mean of 0 degrees Celsius and a standard deviation of 1.00 degrees Celsius. A thermometer is randomly selected and tested. For the case below, draw a sketch and find the probability of the reading, and those given values are in degrees Celsius. So in this case, we're trying to find the probability that the thermometer will have a reading between 0.75 degrees Celsius and 2.25 degrees Celsius. So here's what the sketch looks like. The mean is 0 and the standard deviation is 1. So in this case here, 0.75 is to the right of 0 and 2.25 is to the right of 0. So in this case here, we shade in between 0.75 and 2.25. That's that green shaded area we're going to find. Now, we need the areas to the left of 0.75 and the area to the left of 2.25. So for 0.75, using our standard normal distribution table, go to 0.7 and then 0.05, read across and down. You're going to see it's 0.7734. So in this case here, the area to the left of 0.75 will be 0.7734. Now for 2.25, you're going to find 2.2, and then 0.05 is going to be this column here. So go to 2.2, go across to 2.2, find 0.05, go down to 0.05, you'll see 0.9878. So that's the area to the left of 2.25, 0.9878. Now what we're going to do here to get this area that's in between, we're going to subtract those two. So now if you subtract 0.7734 from 0.9878, you're going to get 2.144. So in this case here, the probability that a thermometer randomly selected and tested would have a reading between 0.75 and 2.25 will be 0.2144. Okay. Okay, and I think I got another example that is related to this one, so let me go ahead and go pull up this one. Let's say we wanted to find the indicated area under the curve of a standard normal distribution and then convert it to a percentage and fill in the blank. So there's this, about blank percent of the area is between z is equal to negative 2.2 and z is equal to positive 2.2, or within 2.2 standard deviations of the mean. Okay. It'll help to draw a normal curve to find out what we're trying to find here. Let's see. Here's 0. Negative 2.2 is on the left. 2.2 is to the right, and that's your z-scale. So, in reality, we're trying to find this area that's in between negative 2.2 and 2.2. Okay. So this is where we use our standard normal distribution table. So for z is equal to negative 2.2, that area, and I'm talking about the area to the left of negative 2.2. So here, let's find negative 2.2, which is here, negative 2.2. And then 0.02, read across to negative 2.2 and down on 0.02, you'll see that is 0.0132. So that area is 0.0132. Okay. Let me double check. Negative 2.2. Oh, I'm sorry. This should be negative 2.20, because that's only to one decimal place. So negative 2.2. Okay. And you have to look under 0.00. Okay. So negative 2.2 and 0.00, that's going to be 0.0139. Okay, so here I need to change this to 0.0139. Okay. Okay, now for z is equal to positive 2, and I'm going to put 2.20 here. Now we want the area to the left of that. So 2.2, we have to look under the positive z-scores this time. So here's 2.2. This first column is your 0.00. So negative 2.2, and then 0.00 will be 0.9861. Okay. Right, so 0.9861 represents the area to the left of 2.20. Now we want to subtract those two. So, in this case, the area between negative 2.2 and 2.2 is this, 0.9861 minus 0.0139. Subtract those two, you're going to get 0.9722. Okay? Now that 0.9722 is a decimal. To change this to a percent, you have to move your decimal point 2 places to the right. So 0.9722 as a percent will be 97.22%. And that 97.22% represents the percentage of that area between negative 2.2 and 2.2. So to answer the question, about 97.22% of the area is between negative 2.2 and 2.2. Or we can say 97.22% of the area is within 2.2 standard deviations of the mean. Okay, now, we've already talked about finding the area when you're given your z values. Now we're going to be working backwards. In this case here, we're going to be trying to find, in this case, the probability, not the z value, given the known area. Okay, so here, I'll do this on another sheet. So here we're going to find z-scores given the known area. We're finding z-scores given the known areas. Now to do that, you have to pretty much sketch the graph. Okay. Now, then second, you're going to use table, which is your normal distribution table. And the way you're going to do that is use the cumulative area from the left. And that's to locate the closest probability in the body of the table. To identify your z-score. Okay. So actually you're going to be using the body of the table to find out what your z-score is, using that standard normal distribution table that we talked about. So to start off with this example, we'll start off with something simple. Here you want to find the indicated z-score. And the graph depicts a standard normal distribution with a mean of 0 and a standard deviation of 1. Okay, so in this case here, we're given the area to the left already, which is going to be 0.8554. That's the area to the left. And it is a number that's bigger than 0.5, so we look under positive z-scores. And how did I know that I had to look under positive z-scores? Well, that decimal value is bigger than 1/2. If it was less than 1/2, then you had to use negative z-scores. That's a hint that you can use there. So, in this particular situation, 0.8554, I looked in the body of the table for 0.8554, which is this number right here, which I just found. And then I'm going to read the z-score off to the left and off to the top. To the left of 0.8554, that's 1.0, and up here will be 0.06. So 1.0 and 0.06 will give me a z-score of 1.06. Okay, and I'll write it like this, because the one on the left is 1.0. The column that is in is 0.06. Add 1.0 and 0.06 together, you're going to get 1.06, which is your z-score for 0.8554. Okay, another example would be this one. Here we want to find the indicated z-score, and the graph depicts the standard normal distribution with a mean of 0 and a standard deviation of 1. Now, just like in the last example, we're already given the area to the left of the z-score we're trying to find, which is 0.1660. Notice 0.1660 is less than 0.5. It's less than a half. So we need to use the one that says negative z-scores for our standard normal distribution. And we need to look in the body of the table for 0.1660. So in this case here, probably have to move this up a bit because I've already found 0.1660. That's right here. That's where my finger is. 0.1660. Then I read the part that's to the left and the column that 0.1660 is in. The row that 0.1660 is in is negative 0.9, and the column is going to be 0.07. I have to move that down so you can see that I'm dealing with 0.07. So in this case here, my z is this. It's going to be a negative 0.9 plus, and they're both going to be negative. So it'll be negative 0.07, which means my z-score is negative 0.97. So here, that corresponding z-value will be negative 0.97 for the area of 0.1660. Okay, next example. Find the indicated z-score. The graph depicts the standard normal distribution with a mean of 0 and a standard deviation of 1. Now notice, they give you the area to the right, which is 0.8962. If you're going to use this table A-2, it does say cumulative area from the left. So, let's find this area to the left. To do that, we're going to do 1 minus 0.8962. So 1 minus 0.8962 would give me 0.1038. So this area to the left is going to be 0.1038. Okay. I had to find the cumulative area to the left because I want to use table A-2 to find that z-score. And the table is for cumulative areas from the left. So that's why I did 1 minus 0.8962. So now I'm going to use this 0.1038 to help me find out what that z-score is. Well, it's less than 0.5, so I have to use the negative z-score portion of the table. Let's find 0.1038. And in this case here, it's right here. I need to move that up some. It's right there, 0.1038. Now we look at the row that's in, that 0.1038 is in. Here's the row that's negative 1.2. The column that is in is 0.06. So here's the 0.06, and then we got negative 1.2. So in this case here, our z will be the negative 1.2 plus, and we have to make that 0.06 negative. So in this case here, it'll be a negative 1.26. That's the corresponding value for 0.1038. Here they give us the cumulative area to the right. So to find the cumulative area to the left, we subtract 1 from that 0.8962. And then we use that 0.1038 in our cumulative area to the left for our standard normal distribution table. Okay. Okay, another example. This one's the same way. We're finding the indicated z-score. The graph depicts the standard normal distribution with a mean of 0 and a standard deviation of 1. Notice again we're given the area to the right of that z value, 0.1685. So the area to the left, this area right here, that's going to be 1 minus 0.1685, which will give me 0.8315. So it's this area to the left that we're going to be used in our standard normal distribution table. And 0.8315 is bigger than 1/2, so we use positive z-scores. And we're going to find 0.8315 in this table. Let's see, 0.8315 is right here. Where my finger is at, 0.8315 is right here. Now we look at the row and the column that 0.8315 is in. The row, in this case, is 0.9. The column is 0.06. Okay? So that z value is this. 0.9 plus 0.06. That's going to give me 0.96. So that corresponding z value for 0.8315 would be 0.96. Okay. So again, that's another example where you had to subtract 1 from the area, 1 minus the area to the right, in order to use that table, because that table calls for the cumulative area from the left. Okay, that's very important. Okay. Okay, let's look at an application of finding a z-score, like this one. Assume that readings on thermometers are normally distributed with a mean of 0 degrees Celsius and a standard deviation of 1.00 degrees Celsius. A thermometer is randomly selected and tested. Draw a sketch and find the temperature reading corresponding to P81. And they call that the 81st percentile. This is the temperature reading separating the bottom 81% from the top 19%. We're finding the 81st percentile. And here's the sketch. and our z-value is what we're trying to find. So in other words, the 81st percentile is going to be this shaded area to the left. Okay. It's going to be that shaded area to the left. So in this case here, 81% as a decimal would be 0.8100. Okay. And it's bigger than 0.5, so we'll go ahead and find now you're not going to find 0.8100 in this table, but you want to find a value that is closest to 8100, and in this case it's going to be 0.8106. Okay, by looking at this, 0.8106 will be the one that's closest to 0.8100. And then we read the row and the column that 0.8106 is in. So in this case, that's 0.88. Okay, so your z-score that you're looking for, that's going to be 0.8 plus 0.08. which is going to be 0.88. Okay, so that's your z-score that we're looking for. Okay, so that temperature reading that corresponds to the 81st percentile will be 0.88. Okay, now another example would be, let's assume that a randomly selected subject is given a bone density test. Bone density test scores are normally distributed with a mean of 0 and a standard deviation of 1. Draw a graph and find P16, which is the 16th percentile. And that will be the bone density score separating the bottom 16% from the top 84%. So in this case here, so here we're looking for the z-score here. And the bottom 16% will be this small shaded area here. And 16% as a decimal, by the way, is 0.1600. So we're going to be looking for a number that is closest to 0.1600. And 0.1600 is less than a half. So we're going to have to, in this case, use the one that says negative z-scores and find a number that's closest to 1600. Okay. And by looking at this, you have to go a little bit further down here. And I found it, 0.1611. It's going to have to be that number that's closest to 1600. 0.1611. And we'll look at the z-value that's to the left and the row in the column that 0.1611 is in. That row is going to be a negative 0.9 and that column is going to be 0.09. So here my z-value is negative 0.9 plus the column that is in, that's 0.99, and that's going to be negative as well. So it'll be a negative 0.99. So negative 0.99 is going to be the corresponding z-value that's in the 16th percentile. Okay. Okay. I think I have another example that is like this one. Assume that the readings on the thermometers are normally distributed with a mean of 0 and a standard deviation of 1.00 degrees Celsius. Assume 3.1% of the thermometers are rejected because they have readings that are too high, and another 3.1% are rejected because they have readings that are too low. Draw a sketch and find the two readings that are the cutoff values separating the rejected thermometers from the others. Okay, so in this particular situation here, we're going to go ahead and draw the normal curve. So we're looking for a z-score on the left-hand side and a z-score on the right-hand side. ZL represents the z-score on the left. ZR represents the z-score on the right. And this shaded area represents the bottom 3.1%. And as a decimal, it will be 0.031. 0. See, 0.0310. And this shaded area to the right, that's also 0.0310. Okay. Now, what I notice is that the area to the left and the area to the right are the same. So if I find this z value, which is this area to the left, the z value on the right has to be the opposite. Okay. So the z-score on the left is the opposite of the z-score on the right. It'll be easier to use this one right here. Find 0.0310. That's less than a half, so let's use the negative z-score table for the standard normal distribution and find a value that is less than 0.0310 or closest to 0.0310, well, 0.0310. Okay, in this case 0.0307. Let's find the row and the column that it's in. The row would be negative 1.8, and the column that it's in is 0.07. Okay, so it'll be negative 1.87. So for this one, that's negative 1.8 plus, and this is going to be negative 0.07, which will be negative 1.87. So that z value on the left will be negative 1.87. Well, guess what? I did mention that these areas are the same. So if this is negative, the other one has to be positive. So it'll be a positive 1.87. Okay? Because their areas are the same. Okay, there is one last thing I need to cover out of this particular video, and that's called the critical value. Okay, because this is an application of finding the z-score when you're given a known area. And I'm going to define what a critical value is, and later on in this course you're going to be seeing this term pop up again because you're going to be finding critical values for numbers. That is a z-score. Critical value is a z-score separating unlikely values from those that are likely to occur. It is a z-score. It separates the values that are unlikely to occur from those that are likely to occur. And the notation for that is this. Z, and that small symbol that looks like a fish, that's the Greek letter alpha. That's the Greek letter alpha. So Z sub alpha, it denotes the z-score with an area of alpha to its right. Okay. Critical value, its notation would be Z sub alpha, and that denotes the z-score with an area of alpha to the right. Okay. So, in this last example for this video, we want to find the indicated critical value of Z sub 0.03. Okay. That 0.03 that you see there represents the area to the right of the Z value, to the right of the critical value. So here, this represents Z of alpha, or Z of 0.03, I should say. And it's going to be this shaded area to the right. So this represents 0.03 here. Now, if we're going to use the standard normal distribution table, we want this area to the left. So if this area is 0.03, the area to the left has to be 0.97. And I'm going to take this out to 4 decimal places. So it'll be 0.9700. So 0.03 is the area to the right, but for the area to the left, you have to do 1 minus 0.03, which will be 0.9700. Now, it is a positive z-score, by the way, because our area to the left is a number bigger than 1/2. So we look in the body of the table and find a number that's closest to 0.9700. And I'm going to use 0.9699 because that's a little bit closer to 0.9700. So we look at the row and the column that 0.9699 is in. In this case, 1.8, and then we'll bring this up. You'll see that the column that 0.9699 is in is 0.08. So we got 1.88. So the Z of 0.03 is this 1.8 plus 0.08. That will give you 1.88. Okay. Alright, now I realize that the video was quite lengthy, but pretty much if you, with these pretty much examples, this should be more than enough to assist you with all the homework that is in that particular section, because it does have, I do have a lot of things that I had to pretty much cover in that particular section. Okay, so that will conclude this particular section on the standard normal distribution. So all I can say here is pretty much I wish you the very best on the homework assignment, and email me if you have questions.